Have you wondered why shuttlecocks don't fly in symmetrical parabolas?
Let's look at the vertical and horizontal components of the motion of the shuttlecock. We will first look at the horizontal axis. For this component, taking forward direction as positive, the weight of the shuttlecock do not affect the motion as its line of action of force is perpendicular to the x-axis. The only force acting in this direction is the air resistance, which is directly proportional to the square of the velocity, shown in the formula on the screen. Taking the origin at the point where the shuttlecock leaves the racket, the resultant force is negative, as it is acting against the shuttlecock. The magnitude of acceleration will decrease until it reaches zero due to decreasing velocity. From the shape of the acceleration time graph, we can obtain the shape of the velocity time graph. Since the shuttlecock has an initial velocity, the graph starts with a positive value, decreasing at a decreasing rate until it reaches zero. Then, from the velocity time graph, we can infer the shape of the displacement time graph. The graph starts with the origin and increases at a decreasing rate. The shuttlecock will continue its horizontal motion until all of its initial energy have been used to overcome air resistance. Next, we will take a look at the y-axis. For the vertical component, effects of a force include weight and air resistance. Taking upwards direction as a positive direction, weight acts in the negative direction and air resistance acts in the direction opposite from the motion of the shuttlecock. We will first look at the acceleration time graph. The acceleration of the shuttlecock starts with a negative value and increases at a decreasing rate until acceleration reaches zero, the point where terminal velocity is reached. When the net acceleration of the shuttlecock reaches negative 9.81 t1, the shuttlecock is momentarily at rest. This is because the net acceleration is equivalent to the acceleration due to gravity, showing that there is no resistive forces and hence no velocity. By understanding the shape of the acceleration time graph, we obtain the shape of the velocity time graph. The initial velocity is positive as the initial motion is an outward motion. Velocity of the shuttlecock decreases at a decreasing rate and continues till it reaches a horizontal line, where the shuttlecock reaches its terminal velocity. When the graph cuts the x-axis at t1, the shuttlecock reaches the maximum height as the displacement of the shuttlecock experiences a turning point. Lastly, the displacement time graph is an asymmetric parabola with a maximum height when time is at t1. The time required to travel from the origin to the maximum height is less than the time required to travel from the maximum height back to the same reference point. This is because when traveling upwards, the resistive forces is acting against the weight, causing the magnitude of the net acceleration to be more than that when the shuttlecock is traveling downwards.
By the impulse momentum theorem, the change in momentum of the shuttlecock is given by the integral of the force on the shuttle with respect to time. When the shuttle is in contact with the racket, the strings of the racket exert a normal reaction force on the shuttlecock, causing the shuttle to experience a change in momentum over a period of time, as given by the area under the force time graph. For the rackets with high tension, the contact time between the shuttle and the racket is lower as the shuttle bounces off faster. As the shuttle experiences a change in momentum in a shorter time, the net force on the shuttle is larger and hence the rebound height is higher at 0.4 meters. For the rackets with low tension, there is longer contact time between the shuttle and the racket, so the net force on the shuttle is lower and this results in a lower rebound height of less than 0.2 meters.